Welcome back to Reconstructing Gravity. Ted Cole again, and this is chapter G11. I'm going to call it Torsional Pendulum. I'm going to tell a story about a very interesting device I built and some attempts I made to do some experiments on gravity. And obviously, I suppose the device I built was a torsional pendulum. And the question was, can I measure Newton's big G? Can I measure that directly? Is that possible? That's what I was going to try to do. But before I describe this torsional pendulum and show my photos and videos of it, I want to do a brief recap of where we are in this overall project and what's yet to come. This whole experimental project on the torsional pendulum was a break in my work, and so it'll be a break in this video series too. Then we'll get back to the main project. The first about 25 videos are on special relativity, which presented a constructive model. So it's a description and explanation of how relativity works in a straight line, constant speed motion, including a description of the physical phenomena going on, which is generally missing in the normal relativity presentations. Then we got into gravity, and there's a series of calculations that work. Gravitational time dilation, why and how mass falls at an acceleration g, correct calculation of starlight bending, and another calculation yet to come on Shapiro delay. That's going to be bouncing a radio signal off of Venus and seeing that time of return is delayed when Venus is almost aligned with the sun, such that the gravity of the sun slows that signal down. And part B of the gravity work has all to do with the space flow model. In other words, we are proposing that space actually moves towards masses at the velocity required to make all those prior calculations work. We have to understand how that's possible. And already we've been looking at the external flow, the motion of space around the outside of a mass, a planet, and discovered that for all those calculations to work, we have to have a flow rate, a decreasing flow rate that decreases at a constant, 12 pi gm, and proposed a light space, dark space structure of space, which could make that possible. But more challenging even than that is a look at the internal flow, a flow of space inside a planet, which is different than the external flow. We have to figure out what that is, how that works, and how it's related to the pressure inside a planet or a star, and ultimately seek a root cause of why this flow happens and at what rate it happens, so that we have a physical explanation for why gravity exists and how it works. So that's about where we are in the overall project, but now let's turn back to this torsional pendulum. This was a project I did looking at timestamps on my photos in 2017. Absolute shoestring budget, a little over $100 US. I put this together, and all right, I'll describe it. This torsional pendulum is not like a regular pendulum in that it doesn't swing back and forth in the usual way. I'll show you what it is. The basic torsional pendulum looks like this. There's a vertical bar supporting a horizontal bar. At the end of the bar, there are some masses. And any motion of that horizontal bar in the rotational direction causes a torque, a twist in that vertical bar. And that twist wants to return the horizontal bar to its original position. So if you set it off away from its original position and let it go, then it'll oscillate back and forth as it returns to the original position. It'll have momentum, so it'll swing through that original position until its momentum is stopped by torque in the reverse direction. So it is like a pendulum in that it swings back and forth. It's just swinging in this different direction. So the idea of the experiment was to see if I could measure Newton's G. In other words, if I have this pendulum set up and I get it to be at its equilibrium position, and then I bring a mass close to one end of this bar, would there be a gravitational attraction between the mass on the bar and the mass I'm bringing in, such that there'd be a force that would apply a torque to that bar and change the equilibrium position of the horizontal bar, leaving, in other words, holding against a steady torque in that vertical bar. If I could measure the angle of deflection, then I would be able to compute the amount of force, and knowing the masses and the distance, I'd be able to compute Newton's G. First, I bought 2 8-pound iron shot-put balls, and one of them is shown here on top of the classic book on gravitation by Meissner, Thorne, and Wheeler. It's the classic book on Einstein's general relativity theory. Very heavy book in its own right. Then I made a couple of slings out of a soft steel wire so I could suspend these balls at the end of the bar. And this was the original design. It was an 8-foot long bar of about 2 centimeter by 2 centimeter pine with extra doubled up layer of wood near the center because of the higher bending stress there, and a suspension truss. Because I knew that if without a truss like this, the deflection of the wood would be very large and probably snap the wood even with the extra support in the middle. So I built a suspension truss over the top of it, and actually when I built that truss, I put tension in it so that the wooden bar bent upwards when there was no load hanging on it, when the balls weren't hanging on it, so that when the balls were hanging on it, it came back to very close to straight. The first wire I tried was too weak. When I tried to hang the pendulum from the ceiling, the wire yielded and just kept stretching until the pendulum hit the floor. Then I tried a second wire, which was a 0.012 inch diameter music wire, which had a higher yield point. So it did not yield, but it still stretched about 2 or 3 inches when I hung the weight on it, just from elastic stretching. In this picture, you can see the 2-wire truss system, and you can see the upward curvature of the bar prior to loading it with the balls. So the truss is loaded up, but the balls aren't hanging on it, so it's got a upward curvature, which is visible out at the end. These are just a few pictures of how this truss strut was attached to the horizontal bar, and everything was done with Elmer's glue and screw eyes. One more photo prior to hanging. Again, you can see the upward curvature of the bar with the preloaded truss. Once I had it hanging, it was the most sensitive mechanical device I've ever seen. First of all, just getting it to balance horizontally, had to add coins, a few coins to one end because it wasn't perfectly centered or wasn't perfectly balanced. But then any slight touch, it was almost impossible to move this thing with your hand and then let it go without giving it some residual push. Even though you didn't want to, it would happen. And it would move very slowly. A small push with a finger, a very light touch, would set it in motion, but it would be almost an imperceivable motion that would take a long, long time for that motion to stop and reverse itself. In fact, it was very difficult to find where the equilibrium position was of this device. Let me show you a graph. This thing had a very long period of oscillation. This is an example. I didn't measure it carefully because it was very difficult to measure a lot of things on this thing. But it would take like an hour, on the order of an hour, almost an hour, for it to oscillate. And swing one way and then swing back the other way. I had to be extremely patient. And I soon realized, well, I needed to add some damping. This whole device had no torsional damping. With some torsional damping, the period doesn't change much, but at least the oscillation settles down. It doesn't just keep going back and forth evenly. And so eventually there was some hope of getting it to settle down and find an equilibrium position. But and the more damping you added, the more quickly that could settle down. So I built a torsional damper. This actually pictured here was the third design I tried, and it used these 12 paddles that were immersed in molasses. And the idea of a damper is to allow motion, but to resist the speed of the motion. So anything's moving, it'll give a resisting force to that motion. But the slower the motion is, the less the damper applies a force. So you can, ideally designed, you can get to a equilibrium position. The damper doesn't leave any bias on it. It just slows the speed of the motion. Here's some pictures of a damper paddle. The device is all broken apart now, but I still have a few relics. And so I'll bring this picture with the damper attached to show where it was in the center, and the tray of molasses underneath, which had to be lifted up such that the damper was down in it. And amazingly, I never spilled the pan of molasses, so I was lucky in that regard. Even with the torsional damper, the torsional pendulum was extremely sensitive. It was affected by the slightest motion of air. And, I went to extremes. I had to turn everything off. The ventilation fan, obviously, the refrigerator fan, television, anything that created heat, the lights, the modem. I blocked all the air ducts. It was never enough to really get a settled condition. And the thing was, still, even if you had a very good condition, it wouldn't never last too long. One time I thought I had a good measurement going, but the sun came up outside and it got warmer. And as that happened, that seemed to affect things too. It was very hard to tell what was affecting what, but it was an extremely sensitive device and very hard to get a stable measurement of anything. Here's a photo of one attempt at a controlled experiment. It just didn't work out. There were too many random variables. I couldn't get the system to, even with the damper, I couldn't get it to be stable enough to find a neutral position such that I could reference deflections. The goal here was to move the bowling ball closer and closer to see if I could get larger and larger deflections, but the system just wasn't stable enough. I couldn't find that neutral point that was really stable in order to make good measurements, consistent measurements. I will show you, just for fun, I'll show you a few of the time-lapse videos I made. These are all dramatically sped up. And so the first one, I bring in a mass and it seems to stop the ball. And the second one, I literally use my own body as the attractive mass, so you can see me move to the far end. Again, time-lapse, sped up dramatically. I moved to the far end and the far ball seems to be drawn towards me. I move to the center, and that seems to stop. Then I move to the close part of the picture and that seems to draw that ball towards me, back to center, and it seems to stop again. It's anecdotal, it doesn't prove anything, it wasn't a measurement. And the last one here, again, the pendulum seeming to respond to my position. And again, it looks like I'm moving around really quickly, but I was just moving actually very slowly, trying not to disturb any air. And the pendulum seemed to respond. The ball nearest to me seemed to be drawn towards my mass. But again, no measurements, no consistency, just a pretty cool anecdotal picture though. Well, I'll wrap it there. Thanks for watching. Please like, subscribe, share, and leave a comment. Today, instead of a music clip, I'm gonna, since I was back in my 2017 time-lapse videos, I dug up this solar eclipse. I went to the solar eclipse in Kentucky, and I happened to get nice weather. So here's the time-lapse video I captured at the solar eclipse. Catch you next time.